Yesterday we can you hear me okay? Yesterday we looked at kind of the preliminary material. We looked at what science is. We looked at the logical basis for science. We see that science is not absolute, but it's an ongoing, changing understanding of nature. And today we want to begin to look at what we know about the cosmos. So we're going to take a tour of the cosmos today, beginning at our sun, and we'll travel out into space, incredible distances. Our solar system will disappear, and we'll go to the limits of the visible universe, and we'll see what we see. And then we'll come back the second hour, and we'll look at what the scriptures say about the creation, and we'll compare with what the scriptures say with what we see. I think you'll be surprised. So, this, who's changing? Oh, okay. We went over this yesterday, and it's the basic thing, I think, that links Scripture with our scientific observations. If we assume that God is all-knowing, all-powerful, and if God, on one hand, is the architect, creator, sustainer of nature, and on the other hand, He is the author of the inspired Word, the Bible, then the Bible and nature have the same creator. And they must be in an agreement, if that's true. So that's my initial premise, and that's the way I look at all of these things. I want to look at a couple of scriptures before we begin. And of course, we want to look at Genesis 1:1. In the beginning, God created the heavens and the earth. We'll come back to this later today, and I think you'll get a deeper appreciation for this one little short sentence. There's a lot of information packed in there in the Hebrew. Secondly, the psalmist 19 says, "The heavens declare the glory of God." And I want to show you the heavens in maybe a way that you haven't seen them before. And maybe this scripture will mean more to you after today. And thirdly, I want to look at Genesis chapter 22, verse 17. Abraham has finally had his long-promised son Isaac. And Isaac is a young boy, or maybe a young man. And God says, "I want you to sacrifice Isaac to Abraham." And Abraham immediately the next day says, got up early in the morning, saddled his donkey, got all the provisions, got Isaac and a servant, and set out to sacrifice his son. And that's easy to read, but it's hard to think about. Who could sacrifice their son? But because Abraham was willing to do this, there's a blessing. Basically, we don't have time to talk about it, but in this scripture, Abraham is asked to do for God what God is going to do later for mankind, sacrifice his son. And so there are a lot of parallels in this, and we could talk about this all day. But I want you to see one thing here that maybe you've overlooked, and I'm sure you're all familiar with this scripture. But because Abraham was willing to do this, and God stopped him, he just wanted to know he was willing, he says, "I will surely bless you and make your descendants as numerous as the stars in the sky and the sands on the seashore." Do you know how many stars you can see in the sky? Remember, this is about 3,500 BC. Not BC. 3,500 years ago from now. 3,500 years ago. There were no telescopes. So how many stars can you see with the unaided eye? You've never gone out and counted stars at night. Well, down through the ages, there have been some guys who probably didn't have anything to do on Saturday night, so they went out and counted stars. And they all count a little less than 2,000. It's amazing, 2,000. So can you count 2,000 stars? It might take a while, but you can count to 2,000. But I want to look at this other thing. As numerous as the stars in the sky and the sands on the seashore. Now, I don't know if you have a beach near here, but I grew up in Florida, a block from the Gulf of Mexico. And this is a picture from where I grew up. How many grains of sand are there? And by the way, the state of Florida alone has about more than 3,000 kilometers of beach like this. And you think about all the beaches on the earth. The sands on the seashore. So I could take you to my home in Florida and set you down on the beach and say, your job is to count every grain of sand here. And if you were a young man, you could spend the rest of your life counting grains of sand, and you wouldn't even have to get up and move very much. So look at the comparison here. It's ridiculous, isn't it? Stars in the sky, about 2,000 that you can see, and sands on the seashore, countless. Did Moses make a mistake when he wrote this? Is this what Revelation is all about? Keep that question in mind as we take our tour, and we'll come back to it after a while. This is a picture of our sun. I don't know, how familiar you are with these things. You can see all these on the internet nowadays, but these come from the Hubble Telescope, most of them. These are called solar prominences. Now the sun is a great big ball of super hot gas, mostly hydrogen. It's so hot that the hydrogen atoms are ripped apart, and the electrons are free. They're negatively charged, and that leaves a positive charge. Rest of the atom we call an ion. So you have this super hot electrically charged soup, and occasionally, and it's rotating, so it creates a magnetic field, kind of like the Earth's, but much stronger. The magnetic field of the sun goes way out beyond what used to be a planet, Pluto. So there are eruptions on the sun occasionally. And this super hot conducting soup comes boiling out, and it can't cross the field line. So it forms these arches. And it'll go up until the magnetic field is stronger than the outward force against the gas, and then it all collapses back to the surface. This can be on the order of 100,000 kilometers across it. It's a very big structure. These are called solar prominences. If the eruption is even more violent, more energetic, then we have what's called a solar flare. And a solar flare is so strong that when the eruption occurs, some of it spews out into space. Millions of kilometers. The solar flare, the material that comes out of the top, even comes by the sun and causes polar storms, what we call magnetic substorms. Creates the aurora borealis and the australis. Solar flares. From the bottom of this flare up to the top here is about 3 times the circumference of the Earth. 3 times around the Earth, this distance from there to there. It's a big thing. If the eruption is even more violent, then it blows huge chunks of this nuclear brine out into space. And I put the Earth here just for scale. You can see this is huge. So the sun is a very violent place, and it's monstrous compared to its planets. But compared to other stars, not so much. Here's our sun. Here's a star, Sirius, Pollux, Arcturus. Keep your eye on Arcturus. Here's Arcturus, Regal, Aldebaran, Betelgeuse. That's an astronomer, not a bug. and Antares. Antares is a monstrous star. I mean, our sun is invisible on this scale. In fact, if we put it in terms of our solar system, here's the size of Antares, here's the size of our sun, here's the orbit of Earth and the orbit of Mars. In other words, if you put Antares where our sun is, it would engulf the first 4 planets, half of our solar system. It's huge. And yet, it's so incredibly distant that it's just a little speck of light in the night sky. The brightest star in the constellation Scorpius. I don't know if you can see Scorpius from this far north or not. You can see it if you go south. But it's a constellation. And Antares is that star right there in the constellation Scorpius. That's a scorpion. It's the only constellation that kind of looks like what it's supposed to be. So, our sun is not such a big deal compared to the other stars. It is special in some ways, and we'll talk about that tomorrow. So you get the idea that we're talking about huge distances here. And so we have to get something larger than a kilometer to measure the distances that we're going to look at in kilometers. Would be like measuring your trip from across Russia, from Europe to the Pacific in millimeters. You wouldn't do that. You would use kilometers. Well, we need something much bigger because those distances are bigger. So I want to look at a few things. Let's consider the distance from Earth to the Sun. 150 million kilometers. It's easy to say. How far is that? You have a feel for this kind of distance? So let's put it this way. When I was a teenager, we used to, what we call in the States, drag race. We'd get cars and we'd see who could go the fastest. And so sometimes we would get up to 100 miles an hour, 160 kilometers per hour. It's pretty fast. So let's assume we have a special car that can take us from Earth to the Sun, and it can go at a steady 160 kilometers per hour. So we take off from Earth, and we drive for hours and hours and hours and hours, and hours turn into days, days to weeks, and weeks turn into months, months turn into years, years turn into decades. Do you have any idea how long it would take you to reach the Sun? 150 million kilometers away, traveling at 160 kilometers per hour. Well, let me put it this way. If you were born the day you left Earth, the day you arrived at the Sun, you would be 106 years old. And that's assuming it had a potty on board and you didn't have to stop to go to the bathroom and you could eat and sleep and all that. You never stop, never slow down for 106 years. It's a long way. But Antares is twice that big, just the star Antares, and it's so far away, it's a little speck in the night sky. So we need something bigger than this. So let's consider something much faster. Something on the order of 300,000 kilometers per second. That's the speed of light. 300,000 kilometers in 1 second. That's 7.5 times around the Earth in 1 second. That trip to the Sun that took 106 years at 160 kilometers per hour now takes 8 minutes and change. We're really going fast. So the question is, how far would you go if you traveled at this incredible speed of 300 kilometers per second for an entire year? 365 days. Well, you multiply a day by 24 hours per day, times 60 minutes per hour, times 60 seconds per minute, and you come up with a number that's pretty big, 99.6 with 12 zeros behind it. In other words, 96 9.6 million kilometers is the distance you would travel in 1 year. Now, I don't have any illustration to illustrate how big that is. It's big. Remember, at this speed, it only takes you 8 minutes to go from here to the sun. We're talking about going at this speed a whole year. 9.6 million kilometers. One is called 1 light year. 1 light year. So that's going to be our unit of measurement. It's just remember, it's unimaginable. It's a distance that we can't even relate to. 1 light year. Nevertheless, some of the things we're going to look at are going to be many light years away. So our sun is part of a group of stars we call the Milky Way Galaxy. And we'll come back and look at the Milky Way and what a galaxy is in a few minutes. But I want to look at some things in our little neighborhood of the Milky Way. Things that are relatively close. If you were thinking of the Milky Way as the city of St. Petersburg, this would be your own little neighborhood. Okay? So this is called a planetary nebula. Now, nebula just means cloud. Planetary is because when they first saw these, they mistakenly thought they were planets. As you see, they're not planets. Nevertheless, the name stuck. But this is a planetary nebula. And what this is the remains of a star that died. So you can see what's left of the star right there in the center. See that? That's called, that's what's left of it. It's about the size of Earth. Extremely dense. Much denser than anything we know about. About 400,000 degrees on the surface. And that's called a little white dwarf. Okay? And this cloud here is what was blown off of the star when it died. So you have the material of the star. As the star cools, it contracts. When things get cooler, they contract. If you have a car and it gets much colder, the tires get a little soft. You have to put more air in, right? So things contract as they get colder. So this star, as it begins to burn out and it gets cooler, it begins to contract. But as you compress gas, it heats up. So the gravity pulling the gas in causes it to heat back up. And it continues to compress and get hotter and hotter until finally it explodes. And this is the result. Now, you notice that this is lit up like a Christmas tree. So where does all that light come from? Are you familiar with neon bulbs? You have neon signs, neon bulbs. Electricity flows through the tube and excites the neon gas and causes it to do what we call fluoresce. It emits light. The same thing is going on here, not electricity, but the radiation from this little white dwarf star is going out and exciting the gas in this cloud and causing it to fluoresce. And each gas has its own characteristic emission or color. So, for instance, hydrogen and nitrogen have a reddish color. Oxygen has a greenish blue color. And this dark stuff you see here is dust. Dust doesn't fluoresce. So where you see dark, it's not emitting any light, that's dust. So we have a lot of nitrogen and hydrogen in this star that died and then exploded. So when you see this planetary nebula, that is evidence of a star that burned out and died. Now this is going to be important later. So these things are all over the sky. This is called the Cat's Eye Nebula. Some astronomers are very sophisticated here, I think. There's the little white dwarf, and this is the clouds, and this resulted from multiple eruptions as the star died. Here's one they call the Eskimo nebula. It looks like an Eskimo with his hood on. And there's the little white dwarf again in the center. This is called the Crab Nebula. I have no idea why. The crab, the crab is, you know what a crab is on the beach? Oh, I'm sorry. Got carried away here. Hold on a minute. Let me get back where I was. Okay, Crab Nebula. This is the Ant Nebula. It looks a little bit like an ant. There's the white dwarf in the center. I have no idea why this structure is like it is. It's a mystery. Some of these things are very complex. So all of these are evidence of stars that have died, burned out. But stars are also born, and there's a different kind of nebula. This is a totally different. Those nebulas were about on the scale the same size as our solar system. This cloud is much, much larger. It's like 10 light years across. Our solar system is a few light minutes across. This is like years across, 10 or so. This is called the Keyhole Nebula. And you can see again, there are gases being excited, and they're fluorescing, emitting light. And they're being excited by embedded stars in this nebula that have been created from the material of the nebula. Again, you have dark dust clouds as well. So if we look at there are areas in these clouds where you can see the newborn stars. This is what's called a star nursery. All of these little blue dots are newborn stars. And you have maybe a little place where it's a little more dense to start with. And so the gravity of this more dense area begins to pull more dust in. And as it pulls more dust in, it gets more massive, more gravity. It begins to pull more dust in, and it snowballs. You know the term snowball. It rolls up and gets bigger. So this grows, and as it gets bigger, it compresses. What happens when you compress? It gets hot. And so it continues to grow and compress and get hotter and hotter and bigger and bigger and hotter and bigger and hotter until it reaches 24 million degrees. And suddenly a nuclear reaction is ignited and a new star is born. So there are all kinds of clouds like this in which stars are being born. This is Orion Nebula. And you see all the colors again. These are different elements. Here's a nebula that shows a bow shot, like occurs around a supersonic airplane. This is a star, and the gas is flowing across here. This is the Eagle Nebula. And you see there's a lot of dust in the Eagle Nebula. But there are stars being born in these clouds all the time. So stars, what I want you to understand is, stars have a life cycle. They're born, they live for a while, they're active, they burn, they emit light, and then they burn up all their fuel, and they die, and they go dark. This is an interesting thing. This is called the Omega Centauri. It's called a globular cluster of stars. And if you look at it in the night sky, it looks like one star. But actually there are 10 million stars here. And they're being held together by a black hole in the center. Now I didn't go that far, but if a star is big enough when it burns out and it collapses, it doesn't explode. It collapses into such a dense structure that nothing can escape. It's such a strong gravitational attraction. Nothing can escape, not even light. And so they call it a black hole. They're very, very massive. And so the black hole here is thought to be something like 10 million times the mass of our sun. And it's holding these stars together. They're circling around it. Omega Centauri globular cluster. So those are some of the things that are in our own little neighborhood of the Milky Way. Now, our Milky Way is what's called a spiral galaxy. Do you have water sprinklers that go around and spray out water. So it's kind of that. It's called an Archimedes spiral. And our Milky Way is one of these, but it turns out there are a lot of them. By the way, until about 1919, it was thought that our Milky Way was the only galaxy, that beyond our Milky Way, space was empty. And then people began to, as astronomers began to see these little fuzzy spots. And they found out that they didn't move. Now, comets are fuzzy, but comets move very obviously. They move very fast, in fact. These didn't move. So they didn't know what they were. And as telescopes improved, we realized these little fuzzy spots are other galaxies like our Milky Way. Very, very, very far away. Millions of light years. So this is a typical spiral galaxy, and you see it looks kind of like a discus that you throw in track and field. It's got the bulge in the center, and then it's got the thinner part out here, and you can see dust clouds in here. If you look down on this from the top, you see the Archimedes spiral, very dense center and material spiraling outward. So this is what our Milky Way looks like. It's one of these. And these are all over the place. This is our nearest neighbor galaxy. It's called the Andromeda Galaxy. It's 3 times the size of our Milky Way. It's huge. And it's traveling straight at us at a tremendous speed. But it's all right. It's so far away that by the time it gets here, we're going to be way over here. The Andromeda Galaxy. This is the Whirlpool Galaxy. Some of these are very beautiful. This has a companion galaxy. And the bigger galaxy is pulling material out of the companion galaxy into itself. So this will eventually disappear. This is a southern pinwheel galaxy. You have to go to the southern hemisphere to see that. This is called the Sombrero Galaxy because apparently some astronomer thought it looked like a Mexican hat. But what it has is a spiral galaxy with this dense dust ring around the outer rim. These are just other galaxies. These things are all over the place. Now, here's a different kind of galaxy. Those are all called spiral galaxies. This is called a barred galaxy because you notice the arms don't come from the center like the others. See, these others, we go back. One. Now go back. Okay. See, these arms are coming from the center. But if we go forward again, you'll see that the arms don't come from the center. They come from this structure that goes through the center, and they come from the ends out here. So it's a different type of galaxy. And astronomers, being very sophisticated, call it a barred galaxy because of this bar structure through the center. And here is the mother of all collisions. Now, when we see a train wreck, we think we've seen something. But think about this. Just try to imagine. Here are 2 objects. By the way, I didn't tell you how big these are. The average spiral galaxy consists of 100 billion stars and is 100,000 light years across. Remember, a light year is 6.9 million kilometers, 1 light year. Now we're talking about 100,000 light years in diameter and 100 billion stars. So here's 2 objects that size, and they're colliding. And you can see the stars in here. They're so far away here you can't see individual stars. But the stars in a galaxy are separated so much that when this collision occurs, the stars don't necessarily hit each other, but their gravitational fields interact. And so what you see here is this smaller galaxy has been jerked over toward the bigger galaxy and leaving behind a stream of gas and stars. It's a very violent reaction, and there are a number of collisions. This is one we just happen to see happening as we go. Now, about 1990, the Hubble Telescope was pointed at a spot more or less out toward the North Pole, above the North Pole. From Earth and from all telescopes we had, this spot was completely black. No stars, nothing, just black, empty. So they pointed the Hubble telescope there, and they took a time exposure, like you do with your camera, hold it open and let it gather light. So the first one they took, they let it gather light for some 13 hours. And what they saw was so surprising, they took a number of others, and some of them have light gathering times of a couple of thousand hours. But the result is this. There is a sea of galaxies out there. It's amazing, the number of galaxies. And this, looking through the Hubble, is like looking through a soda straw at the sky. It's a very small area in the sky. And when they looked at this picture, they realized that it was some 5,000 galaxies in this picture. None of these are stars in the Milky Way. Every speck of light you see in the picture, here we go, yeah, okay. Every speck of light you see is a galaxy, not a star. Every speck of light you see represents, on average, 100 billion stars. And there's some 5,000 specks of light in this one little picture. So they took a picture, in the same way, from the South Pole, found a dark spot, took a picture, and the same result, similar. So based on that, if you integrated this over the whole sky, they estimate that there are some 100,000 galaxies in the sky. The furthest one they've seen is some 13.2 billion light years away. Now, remember how far a light year is. It's 6.9 million kilometers, one light year. Now we're talking about 13.2 billion light years. The universe, the cosmos, is just beyond our comprehension in scale, in mass, in energy. As the psalmist says, it is beyond human comprehension. Now, so, how many stars are in the sky? I think we're at a point where we can estimate the number of stars. So based on taking these pictures from the North and South Pole, seeing the same thing, they decided to conclude the sky is what we call isotropic, the same way every way you look. Based on that, they estimate that the total number of galaxies in the sky is some on the order of 100 billion. So they're on the order of 100 billion galaxies. They're on the order of 100 billion stars in the average galaxy. And so how many stars are in the sky? Well, it's 100 billion times 100 billion, or 10 to the 22 stars. Now what that means is 1 with 22 zeros behind it. I don't know what the name of that number is, but it's big. In fact, if you estimate the number of grains of sand on all the beaches of all the continents of Earth, it's basically that same number. So maybe, just maybe Moses, or whoever told him to write that down 3,500 years ago, knew what he was talking about. In fact, the grains of sand on all the beaches of Earth are on the same order of magnitude as the number of stars in the night sky. And we could have not known that until after 1999. So, hopefully this gives you a little bit better appreciation for the psalmist in Psalm 19:1. When he says, the heavens declare the glory of God. And what I want you to think about is the Creator must be greater than His creation. So we see that the universe is beyond comprehension. And God created it. He's even greater. So, again, I think I introduced you to Werner von Braun earlier. He was a German scientist that came to the States. And look what he says. This man is a very great scientist. And he said, finite man cannot comprehend an omnipresent, omnipotent, and infinite God. Any effort to visualize God, to reduce Him to our comprehension, to describe Him in our language, beggars His greatness. The psalmist in Romans, Paul says, for since the creation of the world, God's invisible qualities, His eternal power and divine nature have been clearly seen, being understood from what has been made, so that men are without excuse. And so we look at the universe, and we see how insignificant we are. Our world is. And we should have some appreciation for the greatness of God. He's not just an old man with white hair in the sky somewhere. He's beyond human comprehension. Von Braun also says, speaking for myself, I can only say that the grandeur of the cosmos serves only to confirm my belief in the certainty of a Creator. The universe revealed through scientific inquiry is the living witness that God has indeed been at work. So that's what we've seen. I want to spend the rest of the afternoon talking about what that means. So there's a question. How did the cosmos come to exist? And actually, there is an assumption in the question, because it assumes that it came to exist. In fact, science didn't believe that for over 1,000 years. They believed that it had always existed. So there are two logical possibilities. Either the universe is eternal, it always has existed and always will exist, never had a beginning, will never have an end. Or the universe is not eternal, it had a beginning. If it had a beginning, then there are two other possibilities. In the beginning, either it created itself from nothing, because remember, the universe is all there is physical that exists. So if it came into existence, then logically there was nothing in existence before. So it had to come, created its own self from nothing, or it was created by something or someone. There are no other logical possibilities. So I want to spend some time looking at these two possibilities. And I think it's significant that the first three words of Scripture are in the beginning. 3,500 years ago, the Scriptures told us there was a beginning. It's interesting that science didn't agree with this. From the time of Aristotle, the Greek, until the 19th century, science believed that the universe was eternal. So eternal means that the universe had no beginning and will never have an end. We want to consider that a little bit. And this could be theoretically be achieved several different ways. And so science went through an evolution of their thought. The simplest beginning, the simplest way of thinking about an eternal universe is what's called a static universe. In other words, it's there and nothing ever changes. Period. But we found out when we studied the galaxies that they're moving apart. We know that stars are born and stars die. The universe does change. So science reevaluated their position, and they came up with another idea. Okay, that's what I just said. Sorry, I got ahead of myself. I'm having a little trouble with jet lag today. So the stars have a life cycle, and they can't be static. So it could be eternal another way, though. It could be what we call in science steady state. So let me illustrate that. This would be true if every time a star dies, and we saw evidence of dead stars, a new star is born. Think of it this way. You have a soccer stadium, and there are 100,000 people there to see the soccer game. But 100 people get up and go out to go to the bathroom. But 100 people come in when they leave. So the number of people in the stadium remains the same. That's what we call steady state. There's no net change. People are coming and going, but the number of people in the stadium remains the same. So if stars are born and stars die at the same rate, the universe remains steady state. Same size, same number of stars, but we know now that there's a new piece of information I didn't tell you. Not only is the universe expanding, but now that we have better technology, we know that it's expanding at a greater and greater rate. It's actually speeding up. So the problem, the universe is expanding. So the next idea was that the universe could be eternal, but it would have to be oscillating. So it expands out and it comes back in. Like if you throw a ball into the air, it goes up, and gravity slows it down until it comes to a stop, and then it begins to accelerate back down. So you would have a big bang, the universe would expand out until this gravity pulls it back in, and it comes back into a great collapse. Another big bang, a great collapse. And so it goes on forever, expanding and contracting, expanding and contracting. We know that's not true now because the universe is not just expanding, it's actually speeding up. And so it's getting faster and faster as it gets further away. It's like if you threw the ball up and instead of slowing down, it got faster. The universe will never collapse. And so now we know, and science has finally come to the conclusion that the universe is not eternal. The universe is not only expanding, it's accelerating. Okay, that's what I just said. I'm sorry, I'm getting ahead of myself. So it's now firmly accepted that the universe is expanding, and it will never stop. And that's what Scripture told us to begin with. There was a beginning. If it's expanding and it will never stop, then it had a beginning and it will have an end. And that's what fundamental science tells us. And we'll go through that later. But the universe is not eternal, and that is the position of science finally. Robert Jastrow is a world-famous astrophysicist, and look what he says. Now there are three lines of evidence, not just one, but three. The motion of the galaxies we talked about, they're expanding and expanding at a greater rate. The laws of thermodynamics we'll talk about later. And the life story of stars. They live, they're born, and they die. And all three of these observations point to one conclusion. They all indicate that the universe had a beginning. So I think it's interesting that after some 3,500 years, Moses wrote down that in the beginning, God created the heavens and the earth. There was a beginning. In the last 30 years or so, modern science has come to agree with what Moses wrote 3,500 years ago. The universe indeed had a beginning. So we'll come back and we'll talk about the beginning some more in the next hour. What happened in the beginning? We can take a break.